Welcome everyone to the Rancho Mirage Library and Observatory. We will be getting started shortly, right at 1 o'clock. But as we're waiting here for more people to sign on, go ahead and enjoy these views from our solar telescope right here. And those are live views right now. And right at 1, we'll go ahead and get going. If you're watching the playback of this, go ahead and jump to the next chapter marker. Welcome everyone to the Rancho Mirage Library and Observatory. My name is Eric McLaughlin, and I'm joined here with...
I'm Lauren Zuckerberg, the Observatory Program Coordinator.
And we're here to welcome a very special guest here today. We actually have Mike Ressler from JPL. We'll talk more about him in a second as we get going. We are here to celebrate the launch of the James Webb Space Telescope. It's hopefully going to be launching here in just a few short weeks. And so we have a lot of excitement building here. And as part of that excitement, if you want to get something more tangible than just being here for this live stream, we actually have a nice packet of information with a lithograph, bookmark, and some other stuff in there. And so if you want one of those, please come by the library and observatory, and at the reference desk, we'll have those, as well as at the children's desk, right?
It's at the reference desk.
Oh, it's at the reference desk. Excuse me. Yeah, so we're excited to be getting you guys some of those things because there's a lot of fun stuff going on with that. We also have a art challenge thing that the James Webb Space Telescope is doing. And we have some things to help facilitate that as well. So come on in for that. But without further ado, our guest today, again, is Michael Ressler. He is the project scientist for the MIRI instrument on the James Webb Space Telescope. He got his bachelor's in physics back in 1986 from the Massachusetts Institute of Technology, and he got his master's and PhD in astronomy through the University of Manoa in 1988 and 92, respectively. He has been working at JPL for quite some time and is currently, as we mentioned, the project scientist for the mid-infrared instrument on the James Webb Space Telescope. He's also the principal scientist for the astrophysics and gravitation group at JPL. He has actually won a number of awards as well. He won the JPL Lou Allen Award for Excellence in 1998, the NASA Group Achievement Award for the WISE project science team, that is the Wide Infrared Science Explorer spacecraft, and he also won the Robert H. Goddard Award for Exceptional Achievement in Science in 2013 and the NASA Exceptional Achievement Medal in 2013. So welcome everyone, Michael Ressler.
Hi, good afternoon. It's a pleasure to be here.
Yeah, thank you so much for being here. We'll go ahead and let you jump right in, but once again, it is an honor to have you here, and thank you so much for bringing this direct link to the James Webb Space Telescope science team here, and we can't wait to have everyone enjoy what you have here. So the floor is yours.
All right, thanks very much, and good afternoon again. I'm here to talk a little bit about the James Webb Space Telescope. It's a project I've been working on for a long time, 20 years for my particular instrument. But we talk about it being a successor to the Hubble telescope. So we need to talk a little bit about Hubble first. For over 30 years, Hubble has had a spectacular impact on the way we understand the universe. It inspires us and amazes us, and occasionally amuses us. This little smiley face, friendly smiley face peering back from the cosmos is a cluster of galaxies, and there are two very bright galaxies, the two yellow eyes in the middle, and the gravity from those galaxies is actually acting like a magnifying glass to some galaxies that are much farther away. Those are the bluish arcs are actually galaxies in the background that are distorted by the gravity of those two galaxies. And so Hubble has taught us a lot about how the universe is formed, when galaxies formed. But there's a lot more we want to know. But Hubble started us on the path to being able to ask a lot of questions. And so even though this picture is kind of fun, it's actually very important for what it tells us about how our universe works. This is a very famous field that you may have seen before. It's the Hubble Deep Field, one of the Hubble Deep Fields, in fact. These are areas of the sky that to ground-based telescopes looked completely blank, but when we stare at them with Hubble for many, many hours, we see just fields of galaxies. Pretty much everything in this picture is a galaxy. The only thing that's a star is the bright red spot with the crosses for the diffraction spikes from the telescope. Everything else in here is a galaxy. And I know you can't really see it in this picture, but if you stare really, really hard, there's a little red spot near the middle that when we look at it with other instruments even, we see this fuzzy blob with the very unlovely name of GN-Z11. This is currently the farthest known galaxy. It's the galaxy farthest away from us, the farthest known galaxy. And we're seeing light from it as it looked about only 400 million years after the Big Bang. So, the universe is roughly 13.7 billion years old. So we're seeing as it looked 13.3 billion years ago. So we want to go find more of these things. And so that's part of what JWST will allow us to do. Hubble also produced lots of pretty pictures, and this is my personal favorite. This is a star, or actually a pair of stars, that's in the center of the picture, where one of the stars is dying. It's actually started to blow off its outer layers. And because there are two stars, the motion around the stars sort of focuses and funnels the material that's flowing away from one of those stars. So the different colors that you see in this picture are colors from different atoms that are in this nebula. It's telling us about nitrogen and oxygen, maybe a little bit of carbon that are flowing out from the star. But to me, it's just very pretty. So, we all know they're very pretty pictures that Hubble was able to produce. So, as I mentioned, Hubble began the conversation about how our universe is formed, but there is a lot more that we'd like to find out. This particular picture is mostly from ground-based telescopes, some of the 8 and 10 meter telescopes that are out on Mauna Kea in Hawaii. They provide the blue and the green colors in this image, but the red colors come from a smaller previous infrared space telescope called the Spitzer Space Telescope. And all the red dots you see in this picture are very distant galaxies that even Hubble can't really pick up. And more surprisingly is these galaxies are older than we expected them to be. We didn't expect so many relatively full-formed galaxies early in the universe. So these are raising all kinds of questions. And so if we want to answer the questions that are being asked by our current instruments, we need to do the next thing. We need to go somewhere else. And so that's what the Webb telescope is designed to do. The James Webb Space Telescope has 4 principal science goals. We want to discover and confirm the first light-emitting objects in the universe. What came first right after the Big Bang? We think they were kind of clusters of stars that eventually formed into galaxies, but we'd like to understand that better. We'd like to actually find them and investigate what was going on. After those first light-emitting objects started to mature and gravity started to pull some of these things together, we assume they formed the first galaxies. So we'd like to understand how those galaxies were actually assembled. Much closer to home, we want to understand the earliest steps of how stars are formed and how planets are formed around them. We'll get into that more in a few minutes, because that's when I get the chance to do science, that's what I study. And then we also want to look at the planets around other stars that we know of to see if they contain the materials that are needed for life. We won't be able to discover life directly, but we can look for those signatures and the things that are needed to support life like we find here on Earth. So those are the 4 main themes of what Webb is supposed to look for. And I guarantee you, whenever you look at the sky with a new instrument, you always find a lot of things that you didn't expect. So even though these are the 4 things that drove the design of the Webb telescope, it's the stuff we have no clue about that's actually going to be the most interesting stuff. Just to compare Hubble and Webb very quickly, Hubble is about the size of a school bus. The primary mirror, the mirror that gathers the light to focus it onto the instruments, is 2.4 meters in diameter. It's about 8 feet in diameter. Webb, because we're going after bigger and tougher questions, is also bigger. It's about 6.5 meters in diameter. The primary light gathering mirror are about 21 feet in diameter. And it's so big, we can't wrap it in a shell to shield it. And so we have this sunshade that looks kind of like the diamond shaped thing that shields the telescope from the sun. And then the telescope itself sticks up from that and gathers light on that big primary mirror. So while we talk about Webb being bigger than Hubble, it's not a replacement. It really is a successor in the sense that it complements and extends what Hubble did, well, what Hubble is still doing, in fact, and what the Spitzer Space Telescope did in the 2000s. But to really address these questions, rather than working at visible wavelength light like Hubble does, we actually need to work in the infrared. So I want to talk a little bit about what's the infrared. We talk about that. What do I mean? What is infrared radiation? So if you pass white light through a prism, you see this very pretty rainbow. We're all familiar with rainbows after a rainstorm. I think they're one of the most beautiful things in nature. But when we look at that, it's very natural to say, what's over here just past the purple light that I can see? And on the other side, what's over there past the red light? William Herschel did an experiment in 1800 where he put thermometers in each color of light after passing it through a prism. And what he found out was that the thermometers got to the warmest temperatures over past the red. So not even in the rainbow itself, but in an area that looked dark just past the red. And that was the discovery of the infrared. Infra means below, so it's below red, longer wavelengths than red light. So it's light radiation that shows up in that part of the area that's infrared. So infrared light has a lot of applications here on the ground. Everybody loves meerkats, so I have to throw in the meerkat picture. This is what they look like. I think this was taken at the Los Angeles Zoo with a normal visible wavelength camera. If we look at them in the infrared, we start to see heat from the animals. And there's a couple things that you'll notice very quickly. One is this guy has a dark nose. That means his nose is cooler than the rest of his face, but he has these really bright white eyes, a little spooky looking. That's because the skin around your eyes is very thin, and so the blood vessels are very close to the surface, so they're warmer than the rest of your face. So, if I took a picture of you in the mid-infrared, you would look the same way. You'd have these very bright eyes. You also notice that the toes are rather dark, so they have cold toes. So I don't know how hot it was that day, but anyway, the bright spots in their fur are just where the fur is a little bit thinner, and so more heat from their body is escaping. So we can learn a little bit about meerkats and their skin just from these infrared images. Perhaps more importantly, or more critical, here's a firefighter who's in a room full of smoke searching for victims. If all he has is visible light to go by, the room looks empty. He can't see through the smoke. But if he has an infrared camera with him, and it is a standard part of firefighting equipment nowadays, you can actually see through the smoke to see that there is a victim on the floor that needs to be rescued. And so one of the properties of infrared radiation is it can pass through dust and particles that shorter wavelength visible light can't. And we actually take advantage of that in astronomy too. So those were a couple Earth-based examples. Now in space, this is a cloud of gas and dust that's sort of floating through our galaxy. And it's closer to us than many of the background stars that you see in this picture. So, outside that little kidney bean shaped cloud, you see lots of stars, but inside the cloud, it seems like all the stars have disappeared, like there's a hole in space. And you'll notice the stars near the edge of this cloud are actually very reddish in color because this dust preferentially absorbs blue light. And then as you go to longer wavelengths, to redder wavelengths, more of the light gets through. So if we look at this in the infrared, the infrared light from the stars passes through the cloud and we can actually see them. So there are actually just as many stars visible behind the cloud as next to the cloud. It's just that all their light is absorbed, the visible wavelength light is absorbed by the dust and we can't see it. So if we go to infrared wavelengths, we can see what's behind that cloud. Now this cloud doesn't have a whole lot going on in it. It's mainly just a cloud of gas and dust. There are other areas though, where this is a picture of the sky in the constellation of Cassiopeia. And it may not be easy to see depending on your computer screens, but there are a bunch of dark bands. So here's a pretty dark band over here, and there's some over here. This is also clouds of dust that are absorbing the starlight behind it. When we go to an infrared image of this region, we start to see lots of little purple and pink color stars popping out. These are stars that are deeply embedded in those clouds that are just a few tens of thousands of years old. They're baby stars. They're stars that are still in the process of forming. So because stars form in these clouds of gas and dust, the only way we can see them is by observing them at infrared wavelengths. We just don't see them at visible wavelengths. And so if you want to study the earliest stages of star formation, you really have to get into the infrared in order to be able to see them. Now you'll notice there's a postage stamp over on the right-hand side of the screen where I still have the visible wavelength picture up. If we also look at that part in the infrared, we see this big red ring, and there is a faint star in the center of that. This is a star that's dying, just like that really beautiful picture I showed from Hubble. In this case, it's a single star that blew off, the outer layers that come out, kind of like a spherical bubble. Well, the material has cooled since it was ejected from the star, so it's cold enough we can only see it in the infrared. It's not hot enough to be seen at visible wavelengths. And so this is where I mentioned, whenever we have a new instrument, you never know what you're going to see. This is an example of that. We didn't expect to see this shell, but it shows up very clearly in the infrared. And so part of the Webb will be taking images just like this, images of star formation regions, galaxies, all sorts of things at infrared wavelengths. Another type of science or another tool of science that it will be using is spectroscopy. And I want to talk about that a little bit. So this is a picture of a tube of hydrogen gas that has an electric current going through it. So the hydrogen is glowing, it's emitting light. But if you looked at that tube in a prism, the same way you get a rainbow from white light, in this case, we only see very distinct colors. We don't see a smooth rainbow. We only see some red, some light blue, and some purplish colors. We call these emission lines. There are colors that the atoms of hydrogen emit light at, and it's very specific. We can actually measure very precisely what the wavelength of each of those colors is. And so, we know hydrogen produces light at 656 nanometers, at 486, and so on. It's a neat property in physics that if you have hot gas that's glowing, it will emit light only at these wavelengths. If you have cold hydrogen, if you have a cold gas that's in front of a white source, it will absorb light only at those same very specific colors. So when we're looking out at the universe and trying to understand what's out there, if we see these colors, whether they're emitting or whether they're absorbing, we know that hydrogen is there. And in fact, every atom has its own unique fingerprint. And so hydrogen has very specific colors here in the red and blue again. Helium has its own set. It has a very bright line here in the yellow. Lithium, oxygen, they each have their own unique fingerprint. And from that, we can identify atoms in stars. So we can say, yeah, stars are mostly hydrogen. They have a little bit of helium and a few other things. In fact, if we take a picture of the sun, its spectrum looks like this. Notice there's a very deep red absorption up here. Well, that's hydrogen. These two lines in the yellow are actually from sodium. I happen to remember that from my graduate classes. Some of the blue absorption down here are those same hydrogen lines that we talked about before, but there are many, many absorption lines in here. So many, many different atoms absorbing things. And in fact, we've detected, depending on who you talk to, 69 or so elements in the sun. Hydrogen is by far the most common, 92%. Helium is in a distant second place with just under 8%. And everything else, the other 67 elements together add up to about a tenth of a percent, maybe 0.2%. Like I said, it depends on who you talk to. But stars are overwhelmingly hydrogen, but we can use those fingerprints to identify all the elements that we see. So breaking the colors down, breaking the light that we see into these different colors helps us identify what's there. But that's not quite the whole story. You've probably heard of redshifts. If you've seen anything about galaxies and the Big Bang. Well, this is a Doppler shift. So anything that's moving toward us, the frequencies of light are shifted blueward. And if they're receding away from us, they're downshifted redward. It's the same general principle as when an ambulance comes roaring by. When the siren is running, it sounds higher pitched when it's coming toward you, and as it goes away, it's lower pitched. So light does mostly the same kind of thing. And so if we observe a set of absorption lines in our laboratory, when we look at a nearby star, they might be shifted just a little bit if the star is moving away from us. But because the universe is expanding, the farther away the galaxies are, these lines are redshifted more and more. So very distant galaxies, what used to be kind of an orangish absorption line, turn on my laser, an orangish absorption line here gets shifted farther and farther out into the red. And by the time we get to this very distant galaxy, this line is shifted off to the right side somewhere into the infrared. So if we want to study galaxies that are very, very far away and compare them to nearby galaxies, everything we know about near-infrared or nearby galaxies gets shifted into the infrared. So we need an infrared telescope to study those same types of galaxies at much earlier ages in the universe. So this is, again, a very powerful tool that lets us understand what's going on much closer to the Big Bang because of all these redshifts. Okay, as much as I love rainbows, they're actually not very good for quantitative analysis. So astronomers plot the intensity of what we see in that rainbow as a function of wavelength. So again, each of the peaks that you see in this plot correspond to some of the bright lines in the spectrum. So it's just a tool that allows us to understand how bright things are relative to each other and lets us quickly identify what the atoms are that are emitting that light. So the problem we have is that works just great for visible wavelengths, but for infrared, we can't plot, we can't show rainbows at all because our eyes don't see infrared. All we get are the graphical plots. So here's a case of a nearby star that's just still in the process of forming. And just like human babies, baby stars are messy. They burp up a lot of material, which we won't go into any more than that. But you can see there's all kinds of things being jettisoned out from the star. But if we want to look at that spectrum to try to understand what the star is forming from, what kind of materials are in the dust, we'd take an infrared spectrum of it. And that looks like this. So remember, visible wavelengths, the wavelength is about 0.5 microns or 0.5 micrometers. So we're looking at wavelengths that are 10 to 20 to 30 times longer than visible wavelengths now. But we actually don't see so many atoms, but what we do see is molecules, so that we can see there's a lot of water ice around this young star. There's methyl alcohol, there's some methane, water ice, carbon dioxide ice, and a lot of what we call silicates. Silicates are basically just a type of rock. Go down to the beach, there'll be lots of silicates over there. So it's the same stuff that we find on Earth. And I have to point out, since we have discovered methane gas in space, cows. Okay, not really. Don't quote me on that. It's a joke. But the point, again, is the fact that the building blocks that we need for life on Earth are things that are relatively commonly found throughout the universe. And our sun and other stars like it form from these materials. Still mostly hydrogen with a little bit of helium. All of this is, down in the noise, so to speak, but it's there. It's part of what our solar system forms from. Okay, so we've talked about imaging and spectroscopy. Another tool that Webb has is called a coronagraph or coronography. If we want to look for planets around nearby stars, the stars are so much brighter than the planet. We need some way to suppress the light from the star itself so we can see what's around it. And so this is an image from about 20 years ago already of the star called Beta Pictoris. It's a relatively bright star in the southern sky. You have to go south of the equator to really see it well. But it's had a coronagraph that's suppressed the starlight in the center. And we see these kind of wings. This is dust left over from the formation of the star, and some of the dust from kind of asteroids grinding each other up. So just like the solar system, we have an asteroid belt. It's sort of similar material, and there's dust left over from that. And so we see it in these bands. We're kind of looking at it at its solar system edge on. Well, the interesting thing is coronagraphs have improved a lot since then. And so if we use a more precise coronagraph, we can do an even better job of blocking the starlight in the middle. And now we can see there's this little white spot over here. This is actually a planet that orbits Beta Pictoris. And I don't remember the overall period, but I do know that 6 months later, it showed up on the other side of the star. So we've actually seen this planet orbiting the star. And so this technique of coronography is very important for Webb as we try to understand planets around nearby stars. The other technique we can use for trying to understand planets around other stars is if we can't actually separate them from the star, if the planet crosses in front of the star, it will dim the light just a little bit. And we can actually see those transits. You may have heard a lot of talk about exoplanet transits. Well, that's when a planet either blocks a little bit of starlight or the light from the planet itself is being blocked by the star. And so if we follow this plot of intensity versus time, when the planet crosses in front of the star, the overall amount of light drops. When it comes back out, it gets a little brighter if the planet's hot. But then when the planet crosses behind the star, then we get just the starlight again, and then the planet comes out and continues on. So if you can measure the amount of light that we're getting from the star and planet together very, very precisely, more precise than we can do on the ground. That's why we have to do this in space. It actually tells us a little bit about what that planet might look like. In this particular case, the planet is very, very hot, hotter than Venus, so definitely would not support light. But we can tell it actually has a fairly thick atmosphere. And so one of the things that we can do with Webb that we couldn't do before is we can actually get an entire spectrum of when the planet goes in front of and behind the star. And so we might actually be able to see things in the atmosphere of the planet, like carbon dioxide in this case. Whereas the techniques we've been able to use so far, we just haven't been able to do that. Okay, so those are the kind of tools that Webb is going to have that we'll be able to use to look at the universe. So let's go back to Webb itself now. So Webb is a 6-meter telescope optimized for the infrared. That's why the mirrors are gold coated. Gold is a very, very good reflector of infrared light. It has 4 instruments that cover from 0.7 micrometers. That's basically red light. We'll be able to see a little bit of visible red light with Webb, but everything else is out in the infrared where our eyes can't see anymore. So we go well into the thermal infrared out to 28 microns. The observatory itself is a partnership between NASA, the European Space Agency, and the Canadian Space Agency. all these things are getting too expensive for one country to do by themselves. So we look for partnerships whenever we can, because it's better for everybody if we work on it together. And it will be launched, hopefully, in December on a European Ariane 5 rocket. This rocket can launch well over 10,000 pounds. I think Webb weighs in at about 8,000 pounds, so it's got plenty of capability. But you'll notice that Webb has to fold up in order to fit inside the rocket fairing. Webb is so big, we couldn't put it on a rocket without having it fold up. So, every now and then you'll hear Webb being described as the origami telescope, because you really do have to fold it up well to get it inside the rocket. So this is sort of the standard picture of what Webb has to go through as it unfolds after we launch it. I like pictures of real hardware, so I'm going to walk you through the unfolding of the Webb telescope after it's launched. So after we launch it, 4 minutes after launch, the fairings that protected the observatory when it was on the ground separate away. And so you see the observatory still all folded up. After half an hour or so, the solar panels begin to unfold so that we can generate our own power. And though we don't have technicians in space to unfold this for us, everything has to work autonomously. So there are motors that do all the unfolding. After 3 days, we start to expand that big sunshade. So they themselves are folded up into what we call this unitized palette structure, because we like making up big, complicated names. But that's the kind of purplish, the sun shield itself is sort of this purplish material you see. It's basically just mylar, little fancier. But that starts to unfold after 3 days, and after total of 6 days unfolding, the sunshade is then completely open. So you can see the sunshade actually has 5 layers. Each layer protects the next layer in from the sun. And so I've heard it described as the sun shield has an SPF of over 1 million, because we need, the bottom side of the spacecraft here is in sunlight, so it's actually at about room temperature. But the telescope itself, we want to keep to about 40 to 50 degrees above absolute zero. So, a huge temperature difference between the sun side and the telescope side. And so the sunshade will be responsible for making that possible. So I use SPF 50. This would be overkill for my skin, but anyway, so that's after 9 days. At day 10, we unfold the secondary mirror. Now this picture looks weird, I know, because when they did the test on the ground, they had to do it on its side. So I rotated the picture over. But the secondary mirror starts back near the primary and then just kind of swings out and locks into place in front of the primary mirror. So light comes in, it reflects off the primary mirror, bounces back up to the secondary mirror, and then back down through a hole in the primary mirror to the instruments. And that's a pretty common design for big telescopes. So having that double fold. So that's 10 days. After 11 days, one of the primary mirror segments, so there are 2 wings. So the first of the 2 wings begins to fold into place. Day 13, the other side folds into place. And so after 2 weeks, the full telescope, and you have to imagine the sunshade expanded. There's no picture of them all expanded together. So, but anyway, after 2 weeks, the telescope is fully unfolded. Now, there's still other things that are being deployed, so it's about 3 weeks before everything is finally in its place and ready to move on to do other things. So the Mars guys like to talk about 7 minutes of terror when they're landing their spacecraft on Mars. We've got 3 weeks of terror while we're trying to unfold the observatory. So those guys are amateurs. Okay. Webb is going to be placed into orbit around the sun, technically, about 1 million miles away from the Earth. There are some very interesting points between the Earth and the sun. where gravity balances very nicely. So one of those is called the second Lagrange point, and it's a really great place to put spacecraft. And so Webb will be there, and it is about 4 times the distance of the moon. So if you do a little bit of figuring, that means we can't get a spacecraft to it to service it. So unlike Hubble, we can't service the Webb telescope. So part of the reason it's so expensive is because we've done a lot of testing to try to make sure that everything is going to work when it has to. So it will be about 1 million miles from the moon, rotating or revolving around the sun along with the Earth. They'll kind of stay in a straight line as the Earth sweeps around the sun. But it is a really good place for infrared telescopes. Okay, so we mentioned that Webb has 4 instruments on board. 3 work specifically in the near infrared. NIRCam is our main camera, and it works from roughly 1 to 5 microns. It also has coronagraphs. It was built by the University of Arizona. The near-infrared spectrograph is our workhorse spectrograph. So it will do spectrometry from 0.7 to 5 microns. It can actually slice up a field of sky and get many, many spectra all at the same time. So you can imagine if you have a cluster of, say, 50 galaxies, you can actually get spectra of almost all those galaxies at the same time by some of the optical tricks it uses to sort of slice and dice the field. So it allows us to do a lot more work per unit time than traditional spectrographs might have done. And that was designed and built by the European Space Agency. The near-infrared imager and slitless spectrograph was built by the Canadian Space Agency, and it helps actually guide the spacecraft. So when we're pointed at an object, it locks onto nearby stars and makes sure we stay pointed correctly. And it also does some very interesting specialized imaging and spectroscopy that complements what the other 2 instruments are doing. It's a little too detailed to get into here, but the 3 instruments together make up a very powerful suite of near-infrared instruments. And then there's the instrument I worked on. So I'm going to show a picture because, hey, it's what I've been working on for the last more than 20 years. So it works at what we call the mid-infrared wavelengths from 5 to basically 28 microns. And because we're the only mid-infrared instrument, we do imaging, we do spectroscopy, we do coronography, we do everything. So this is the one instrument that will do the longer wavelength things. Now, I was specifically responsible for the detectors, for the sensors that we use in the instrument. And in every picture of MIRI I've ever seen, they've always hidden my detectors on the backside, underneath or something. So a little gratuitous self-promotion. Here's one of our sensors. I'm the big goofy looking guy on the right side of the picture. Kalyani Sukatmi was our manager responsible for getting those sensor modules built, and later became the project manager of MIRI directly. So she's played a huge role in getting MIRI put together, at least the JPL half of MIRI put together. I mentioned that Webb is a partnership. Well, so is our instrument. MIRI is a 50-50 partnership between NASA and ESA. At JPL, the Jet Propulsion Laboratory, we did the work for the NASA side, and 24 astronomical institutes in 10 European countries contributed the European half. So if you're a manager, that sounds like a nightmare, but we had a really great team, great people on all sides. And so it was a real pleasure meeting and working with our European counterparts. And if all goes well, we'll have a really great instrument to use once we get through launch. So you might ask why we have 4 instruments. Why do we need all these things? Well, we really concentrate on different kinds of science. And so the questions that we're answering need several different ways of trying to answer them. So in the near infrared, remember we talked about redshift and how galaxies that form shortly after the Big Bang will be redshifted into infrared wavelengths. So with the near infrared, we'll see ultraviolet light from those galaxies. So what's infrared light in our galaxy gets redshifted into the infrared. And so they'll see the ultraviolet light. But in the mid-infrared with MIRI, we'll see the visible light that got redshifted. So, ultraviolet is much higher or much shorter wavelength than visible light. So, we get the visible light, they get the ultraviolet light. In the near infrared, you tend to see more atoms and very small molecules. And in the warmer or higher energy conditions, in the mid-infrared, we see them in low energy conditions. We see them in more Earth-like environments. That's why we can see ice in the infrared, because it's cool enough to be able to form ice. So in the near infrared, you'll see more mature stars that are in the phase where they're starting to form their own planets. In the mid-infrared, we'll see much younger stars that are still themselves forming. So they haven't had a chance to form planets yet because the stars are still forming. And then also when you're talking about planets around nearby stars, near infrared will concentrate on hot planets that are pretty close to their stars. In the mid-infrared, we'll see more distant planets that are at more Earth-like temperatures. So all four instruments really work together well to allow us to understand and interpret what we're looking at. Okay, just the last few things here. By virtue of being the JPL project scientist for MIRI, I actually get a little bit of my own time to use Webb to do whatever I want. And so I'm doing 6 small little projects, and one of them features this little planetary nebula. So planetary nebula, it's the outer layers of a star that's dying. It blew off those layers. And this particular planetary nebula has the name NGC 1514, not very interesting. But I first became acquainted with it actually with my own little amateur telescope when I was camping down in the Anza Borrego Desert, just a few miles due south of where the library and observatory are. And I was just fishing around and I noticed this fuzzy star near a few other stars, and I figured I was just getting tired. But I looked back later and realized that, yes, it actually is this planetary nebula that was first seen by William Herschel in 1790. So, hey, that's kind of cool. Well, I'd been involved in another infrared sky survey mission that Eric mentioned at the beginning, the Wide Field Infrared Survey Explorer. And I thought, well, gee, I wonder what it looks like to WISE. So let's go look at the data. And when I did, I saw these rings around the nebula. It's like, what are those? So remember I told you that whenever you look at the sky with something new, there you always discover things that you never ever expected. Well, this is one of those cases. No clue these things existed. We still haven't found anything else that looks quite like this. So one of my little projects with Webb is, oh, there's some information about the rings. They're cold, amongst other things. So, one of the things that I thought I would do with Webb is, well, since I can do what I want, let's try to see if we can figure out what's going on here. So I have a few hours devoted to looking at NGC 1514. What are the rings made of? Is this the same stuff as the interplanetary nebula? So, this green part of the nebula in the center looks pretty much like the visible wavelength nebula does. It's only the rings that are really different. So what are the rings made of? Are they expanding the same way the rest of the nebula is expanding? Are the rings really at 160 Kelvin? The WISE measurements might have been contaminated by emission from some of those atoms and molecules that we talked about. And WISE was a very small telescope. It was only 40 centimeters in diameter, 0.4 meters, whereas Webb is 6.5 meters. So with a much higher resolution, will the rings still look this fuzzy? Will they get sharper? Just what's going on there, what we can answer. Now, it's kind of funny. This little square that you see in the center is the whole field of view of our spectrograph. But the interesting thing is that the imager actually looks at a slightly different part of the sky. And so while I'm getting a spectrum of the central star, I can get an image of some of the rest of the nebula. And so if I plan things carefully and take spectra at various parts of the nebula, I can almost get full images of the rest of the nebula. So even though this nebula is so big on the sky compared to MIRI's field of view, I'll still be able to get hopefully a pretty picture of the whole thing, as well as being able to answer all those questions about what's going on in there. Okay, Webb's current status, all testing is complete. We've tested it here in the US during final assembly to make sure everything is working correctly. It was then shipped down to Kourou in French Guiana, where the European Space Agency has their launch facility. I mentioned it will go up on a European Ariane 5 rocket. That's their primary launch facility. So it was actually shipped by boat. It left Seal Beach and went through the Panama Canal on its way to French Guiana. Interestingly, in the lower right picture, they actually just drove the whole truck onto the boat. So that white cylinder sort of thing in the back is the shipping container for the observatory itself. And they just backed the truck in, and then when they got to French Guiana, they just drove it right out. And in the lower left here is when they're pulling it out of the shipping container in one of the clean rooms down in French Guiana. So it's just about ready to get hoisted up to the top of the rocket. So everything is there, and we're on track. So if all goes well, December 18th, 4:20 a.m. Pacific Standard Time is when JWST is scheduled to launch. And so hopefully that will happen finally. So today is L-34 if you keep track of such things. So, as I mentioned, we've been working on MIRI directly for 20 years, since 2001. I actually began a concept study for a mid-infrared instrument for the next generation space telescope in 1997. So I've personally been working on this for 24 years, and I am very, very eager to see this thing launch. So 34 days, fingers crossed. I'd be very happy to take questions. Thank you for listening. And Eric and Lauren, back to you.
Thank you so much, Mike. That was a wonderful presentation. We do already have some questions coming in, but for anyone watching, if you have a question, feel free to hop in the chat and send them over, and we'll start addressing those.
So Eric, I can't hear you.
Thank you. That's right. We have different mutes. Yes. So thank you again, Mike, for your wonderful talk. I was just mentioning that we have room for questions in the chat. So hopefully people will start putting some more in there. We already have a couple of questions at the moment. And so we can jump right in with the first one, which is, how big of an issue are micrometeoroids striking the primary mirror of the JWST?
So that's a great question, but it's actually not the primary mirror we're worried about the most. We're actually worried about the sunshade even more. If a micrometeoroid impacts the sunshade, it's going to poke a hole through there, which will allow a little bit of sunlight to creep toward the back end of the observatory. And that will warm things up a little bit. So, we're actually very concerned about those little holes accumulating over at the time, raising the effective temperature of the telescope, raising our background to the point where it will actually cause, particularly MIRI, a lot of trouble. So we have done studies, of course, with the expected rate of micrometeorite impacts and how that will degrade the sunshade and the surface of the primary mirror. So we should be okay for many, many years of operation. But yes, it is definitely something that, is a concern. It's more than a guess. We have done studies to make sure that, in all likelihood, we'll be able to go for at least 10 years with this. I hate to hex it, but we could get very unlucky and something bigger than usual strikes. But, we should be okay.
Thank you. That's great.
Thank you. And that question was from Ron Treat. This next question is from user California Adventures, and it's
And that question is, what will we see if we look at the nearest stars?
So the nearest stars are where we want to look for planets. I know there's a proposal accepted to look at Alpha Centauri, which is very close by and very, very, very bright. Yeah, we built this magnificent, huge space telescope to look at the faintest things in the universe, and they still want to observe the 10 brightest stars in the sky. But those nearby bright stars is our best chance for seeing other planets, other solar systems up close and personal. So, like I said, I know there was a program accepted to look at Alpha Centauri, to look for planets around it. And so the nearby stars, that's what we're really going to be after. It's not the stars themselves, it's any planets that might be around them.
Awesome. Thank you.
Yeah. All right. So our next question is, so with the construction and moving of this telescope, has there been any coating put over the gold to protect it during launch and construction?
No, so the gold, it's bare gold. Gold is actually very resistant to almost everything, so we don't have to worry about corrosion of the surface. We do have to worry about dust. So particularly my house gets very dusty very quickly. So the observatory was assembled in clean rooms where the dust levels are very, very small, very, very tiny. And in that shipping container, you can't really see it in the pictures I showed, but it actually has a bunch of gaseous nitrogen cylinders on the front that purge the shipping container with dry, clean nitrogen to make sure that even in the shipping container, we don't pick up any dust or other contaminants. So, and we can clean it before we launch it as well. I don't think there's a cleaning procedure scheduled for French Guiana, but it was cleaned at least twice during various phases of assembly here in the States. So the gold is bare, but we've done everything we can to make sure that surface stays really clean and dust-free.
Excellent. Thank you.
So our next question that comes up is,
Will you continue working with JWST after the launch and those initial scientific projects you talked about, or is there something else in the pipeline?
Okay, so I mentioned my own guaranteed time. Most of those observations will be done in the first year. I'm also involved in a few proposals that other people have been awarded time for, so I'll be doing a little bit of work with those as well. I am starting to work on something else too. About a year ago, I started working on a mission that's in its early phases of development to look for near-Earth asteroids, asteroids that might impact the Earth. So kind of interesting connection to the micrometeorite question.
Yeah.
So I'll be working on that as well. But yeah, I hope to use Webb for at least a couple of years once it's out into the normal science operations. I didn't in the talk, but I should point out it will actually take us 6 months from the time of launch before Webb is fully ready to do science. So that's what we call our commissioning period, where we check everything out. So I mentioned it takes 3 weeks for everything to unfold and get into place. Well, we still have to wait for the observatory to cool. It will actually take 3 months for the observatory to get cold enough for MIRI to start doing any of its commissioning activities, any observations at all. And then once it is cold enough, then we have to check to make sure everything is working correctly. We need to make sure our images look good. We need to make sure our spectra look good. We need to make sure that the observatory points correctly. There's many things to check out. So if we launch in December, by about next June, that's about when we'll start to do the actual science programs for the first year of observing.
Excellent.
yeah. So we got time for a couple more questions. So last chance if you want to put some questions in the chat there. Oh, I think we got another one actually right there. So we'll jump straight to that one. Let's see. It is, would it be useful to look at close comets? Like, oh goodness, I'm not going to mispronounce that name. We're just going to let the pop up here say it. There it is.
All right, so close comets, probably not. When comets get close enough to look like the glorious things like Comet Neowise from last year and so forth, that's just way too big for our field of view. So we would be able to look at the nuclei of comets. James Webb is a really big telescope, and so it doesn't move very fast. We can actually track on Mars. Anything closer than that will probably be moving too fast for us. So we could look at comets when they're out near Jupiter, which is probably a pretty good time to start looking at them. That's when they start becoming active. And so getting spectra of comet nuclei as they're coming in or as they're going out would be a great time to look. I don't know if any comet proposals were approved. The problem with comets is we never really know when they're coming, so they're hard to schedule in advance. But I'm sure that if there's some interesting ones that are coming through, there might be some target of opportunity observations to go catch them. But yeah, close is not so good. Catching them when they're a bit farther out is when Webb will be able to do the best work.
All right, great. Yeah.
Excellent.
Our person asking the question notes that this one's not coming closer than Jupiter, and it's in 2031. So that's promising.
Well, maybe. There will be others.
Yeah.
Yes.
Yep. And our last question comes from Ron once again. Will the Webb help resolve the discrepancy on the expansion rate of the universe?
Well, the folks that do that work certainly hope so. That is probably it probably is the biggest unresolved question in cosmology, at least right now. I'm sure there will be more once we do resolve it. But certainly the fact that we have two very good methods of measuring Hubble's constant that disagree by so much. It may not seem like a huge disagreement, but it's big. It's big in terms of what our data are telling us. And so Webb will certainly help. I'm not going to promise that it's going to solve it, because who knows? Nature might throw us at a real monkey wrench here. But certainly many programs that Webb does will in some way touch on that dispute. So hopefully we'll get it nailed down. But like I said, I don't want to promise.
Very good. All right. Well, thank you so much, Mike. We'll be right back with you in just a second. Just want to one more time let everyone know we have packets here at the observatory the library and observatory. You can get them at the reference desk. You can get a lithograph of the James Webb Space Telescope, mission sticker, as well as some information on spin-offs and some good sky charts. So feel free to come on by and explore some more with the James Webb Space Telescope as we get ready to watch that launch. We're very excited to see that coming in. So once again, thank you, Mike, so much for all the information you gave us today. It was fascinating to go through all this with you, and we look forward to seeing where James Webb Space Telescope goes and what cool research comes from it. So thank you.
Thanks for having me. It was a pleasure to be here.
Yeah, once again, pleasure and honor to have you. All right, everyone, thank you so much for joining us here at the Rancho Mirage Library and Observatory, and a thank you to the Rancho Mirage Library and Observatory Foundation. It's through that foundation that we're able to help set these things up and move forward with things here. So once again, thank you to that. And everyone, make sure you get ready and get excited for this launch. Anyway, bye, everyone.